Alright, so here we go. We got number 20 here about the human-powered aircraft. Alright? Pedal bicycle produce power output of 0.3 horsepower, which right away we know we have to convert into watts. And it's low cost. How much energy does the pilot expend during the flight? And then how many candy bars would that be? Alrighty. That's kind of pretty straightforward. What did people have for their Y for this? Ooh, that's too big. So, any thoughts? What did somebody have? Who's brave, trustworthy, and true?
Straightforward, I said the pilot doesn't work when pedaling.
That's a great way to start. Pilot does work when pedaling. Something like that. I think I need to make this a little bit thinner still. I would also put in there that power is the rate work is done. That's probably that and the pilot doing the work when they're pedaling are the two crucial ideas in this one. Oh, you want me to? Okay, yeah. Equation-wise, going to that's not what I wanted, this is what I wanted. My equation sheet, I can look at my equation for power, and I'm looking at the work over time version of it. Huh? Sure. How's that? Not better? So I'm looking at the power equals work per time. So that's the one I'm going to start off with. Make sure my width is correct. So power equals work per time. And they tell me my power, right? My power is 0.3 horsepower. And a horsepower equals 746 watts. So my power is going to be 0.3 horsepower. That's very large. 0.3 horsepower times 46 watts per horsepower. 223.8 watts. Thank you. That's the power there. And they want to know how much energy does the pilot expend during the flight. And the time that they're traveling for was 2 hours and 49 minutes. That's where we have to do some conversion there, because they want to know the energy or the work, so we're going to rearrange this to be delta work equals power times delta time. Right? A little algebra in the morning. But our time, looking here, they want our answer in, what's that big M stand for? Megajoules. So they want it in millions of joules, right? Mega is million, mega millions. Yeah, it says millions, millions. Sorry, Caitlin.
So how would you change
So I'm going to convert my time to seconds because I've got my power in watts, which is a joule per second. If I can convert this time to seconds, then I can get joules, and then I can convert them to megajoules, or change my unit to joules, right? Because I'm going to go through it. There's like 2 steps. Okay. So I already have my power in nice metric units of watts. My time I need, so they're telling me my time is 2 hours, 49 minutes. So I need to get that into seconds. So to get hours, give myself a little more room here. Get hours to seconds, so I do 2 hours times 3,600 seconds per hour plus 49 minutes times 60 seconds in a minute, and I get that conversion, which is 78,000 something. Yep, that's what I get. 10,140 seconds. Now we can actually do the work. Now we have everything in the right units. So delta W equals my power, 223.8 watts, times my delta time, 10140 seconds, and I get and I'm going to divide by 1,000,000. And I'm going to get 2.27 times 10 to the 6th joules, which is 2.27 megajoules. Okay. All right, so that's part 1. And then part 2. Do we need to do part 2? I mean, because it's really just conversions, right? So we've got 1 calorie, food calorie equals 4,186 joules. And each candy bar is 280. And they want to know how many candy bars. So 4186. So all we're doing here is taking our answer, so we're going to take the amount of work and convert it from joules to calories, and then convert that from calories to candy bars. Right? Remember, conversion is just not changing the amount, just so you multiply it by the number 1. So let's see, there was what, 4,186? Okay. So 4,186 joules in a big cal, and each candy bar had 280 cals. Right? I'm assuming you guys can multiply, right? Should you use megajoules or joules? Joules. Well, one big cal, which is a kilocalorie, equals this many joules. But it's 280 big C cals. Those are also sometimes called food calories or nutritional. Ooh, make it feel good. Should work. So on to 15 here, but this is one where your Y should be a force diagram for it. Because that's going to be the best way to show your understanding of the principles here. So, bow of ship, stormy sea, crew member who's bored, standing on a bathroom scale, and gets 3 different readings, and we're asked to, what's the upward acceleration, what's the downward acceleration. Alrighty, so this is number 15. One idea I would express in here is scales measure what? No, not weight. Normal force. Remember that video about the 2 guys in your head? Yep, that was that. See, I just see that. It was right there. Yeah. So we just got trained through to know normal force on that one. Alright, so let's see. Draw my guy 3 times. We'll make him up. We'll do the base drawing of him the 3rd time. Alright, so if you can't do stick figures like I do, you can always do a block like that, right? Okay. So let's pretty color. So here, in all of them, he's going to have his weight down. And I'm using mg for his weight. What else could I use? Take advantage. Have more fun on the weekend. I could have said f sub g, right? That's Friday. I'm using mg. No, I'm not changing. You know what? I'll do it on this one. Just to appeal to all our learning styles. How's that? And then, of course, I have the normal force, which is what our scale is measuring. And our last part, we're accelerating up and down, and here I'm going to write acceleration equals 0 so that I remind myself I'm not accelerating. Good? Sum of the forces is MA, Newton's second law, right? Let's do these in the order that they asked for them in. They asked for acceleration up, down, and then not the other way. So we'll do the first drawing first. So, some of my forces, which way do you guys want to call positive? Up. Okay, so some of my forces, upwards I have force normal, so I'll make that positive. Negative mg, because it's down, equals m times positive a. Oh, wait a minute, I know mg Because if it's not accelerating, that equals the normal force, right? So in this one, force normal equals the weight. In this one, I expect the force normal to be greater than the weight. And here, I expect the force normal to be less than the weight. Right? So, my force normal is my scale reading. So when I'm accelerating up, would be my maximum, so 930 newtons. That's why it's good to make sure you think here, because up would be my maximum, it's going to be bigger than the weight. Down would be my minimum, it's less than the weight. When it's calm, it's equal to the weight. That's how I can figure out which numbers to use where. So 930, 755. So this is 930 newtons minus 755 newtons equals, I don't know M. SpaghettiOs. Wait a minute.
Wait, hold on.
Wait a minute. F sub G equals mg, right? 755 newtons equals m times 9.81 newtons per kilogram.
Oh my goodness.
Because my calculator is all the way 2 feet away from me, I'm just going to put in that. And then solve for A. And then for the second part, exact same way, except now I have, and so I still have force normal minus mg equals m, but now times negative A. Because the A is now pointing downwards. All the same substitution, but make sure you have solved for A. You guys think you can do the algebra there? Now you see it? All Helen's fault. All right, number 6. Number 6. This is the one about the chameleon and its tongue. One thing I should watch right away is, ooh, they're throwing centimeters at me, right? Find the magnitude of the tongue's acceleration, assuming it's constant. Tell me something we know about the starting conditions of the tongue. It's at rest. So, there you go. Is it the tongue? Yes, tongue. Okay. Starts at rest. Accelerates the whole time, the whole distance. And they want to know what the acceleration is. So one of the reasons I forgot the word whole. The whole distance. They don't tell me anything about time. So in my why, I'm kind of trying to stay away from the idea of time. Because while it's true it accelerates for the whole time also, I don't want to go down that road because I don't know anything about it. So if I can avoid finding out anything about it, that'll be good. And this is where it comes to picking and choosing from the equation sheet. I want to go a little bit smaller here. Caitlin, can you still see that? Okay. So I don't know anything about time, so I'm going to avoid if I can, the definition of acceleration. And I'm also going to avoid my main kinematics equation. And I'm going to gravitate towards v final squared equals v initial squared plus 2ad because it doesn't have any time in it. All right, so I'm going to see if I can use that one rather than all these that involve time, because if I have to find, I would have to find the time and then come back and do the problem. So let's use v final squared equals the initial squared plus 2a delta d. Most common mistake is is forgetting that they're squared. Oh, it does tell me time. What am I thinking about? I don't know. Whoa. So, complete change of plans. No one caught that. So I'm going to also change this to the whole time. Well, that opens up a lot of possibilities. So, let's see if I can use this one just above that, because that's a lot simpler, right? Do I know the speed the tongue ends up at? Oh, good. What would 10 seconds measure? Would that measure the final speed, the final location, or the time? 10 seconds. Time. Okay. So, do I know the final speed or velocity the tongue ends up at? No. Do I know the speed it starts with? Yes. Do I know the acceleration? No. So let's abandon that one just because there's two things already in there. Look at the center one. Do I know where the tongue ends up? Yes. Do I know where it starts? Yeah, in the chameleon's mouth. Do I know what speed it starts with or velocity it starts with? Yep. Do I know the time? Yep. Do I know the acceleration? No. Do I know the time? Yeah. So let's use that one, just one unknown. So I'm going to write out d equals d naught plus v initial t plus 1/2 a t squared. Those should have been deltas, sorry. It ends up at 0.16 meters. I'm going to say where it started was 0 meters. The initial speed is, I'm just going quick because of the time, 0 meters per second. The time was what, 0.1 seconds? Yep. 0.1 seconds plus 1/2 a 0.1 seconds squared. Oh, I can simplify that, can't I? 0.32 meters equals a times 0.01 seconds squared. I think you can do the rest of the algebra. If not, Helen can help you.